Okay, so let us now solve the exercise problems at the end of section 1.2. So this is the first one. Here we are given 4 mappings and we have to determine whether each one of them is one-to-one or onto, and at the same time for any for any element in the second set we have to determine its inverse image under the mapping sigma. So let us start. So in the first one, our first set or domain is the set of real numbers, and the second set is the set of non-negative real numbers, and the function is the square function. So this function you clearly know this is onto but not one-to-one. So we are at the same time, since we have to determine the inverse image for any element in the second set also, let us write it like this. Sigma is onto because for any t belonging to t sigma inverse is equal to okay. So here what we have written is that for any t belonging to t, that means thus for any non-negative real number t, it has 2 square roots which are actually the inverse images of t under the function sigma, and here note that we are denoting that by a symbol which actually Herstein has not defined. It is cumbersome to keep writing the inverse image of an element under sigma again and again. So it's better to use a symbol or a notation for that. Since this is something we are using, we have invented ourselves, although it is available outside of this book. So we have to mention it here, where T sigma inverse denotes the inverse image of T under sigma. And why am I saying that sigma is onto? It's because every element is the image of some element. That's why it is onto. Or in other words, because the inverse image of every element in the second set is non-empty. And it is coming from the fact that every non-negative real number has square roots. If t is non-zero, then there are 2 distinct square roots. If t is 0, there is only one square root, which is 0 itself. So from that we are concluding that sigma is onto, and at the same time we have found the inverse image also. Sigma, you know very well, is not one-to-one, because -1 and 1 both have the same image. Their squares are equal to 1, although they themselves are not equal. Okay, so this is part A. Like that, let us now look at part B. In B, everything is almost like what we had in part A. The only difference is that now S is also the set of non-negative real numbers. It's not the set of all real numbers. So now this will change the situation. As far as ontoness is concerned, we will still have the function onto, I said function. Actually we are supposed to say mapping, but you already know that functions and mappings are same thing. Whether Herstein did not mention functions or not, that actually does not matter. So here the function will be onto, but at the same time now it will be one to one, because these two two elements whose images are T, this situation now will not arise. That is because in S we cannot have this element, when particularly when T is non-zero. So there will be only one element. So we are going to write it like this. Sigma is both onto and one to one, because for any T belonging to T, we have T sigma inverse equal to this, the positive or the non-negative square root of T exists for every non-negative real number T. Note that ontoness of sigma is coming from the fact that this set is non-empty, and one-to-oneness is coming from the fact that this set has exactly one element. Okay. Or I should say at least one element. And so here everything has already been written about. So we come to part C. Now both S and T are the set of integers, and we have this. Now in this case our function will be neither one-to-one nor onto. Why? Sigma is not onto because, say, or let us write it more simply, because there is no integer s such that s square is equal to -1. Now -1 is an element in T, because -1 is an integer, but it's not the square of any integer. So that's why the function is not onto. And sigma is also not one-to-one, and the reason you already know. Here we have taken integers themselves, so we can write the same equations here. Both these integers -1 and 1 have the same image, because the formula for the function is same. It's just like B, only the sets are different. Okay, we still have to find the inverse image of every element in T. Now for any T belonging to T, we have, okay, T sigma inverse. It will be, this set will be empty if T is not the square of any integer. Okay, so let us write that first. This set is empty if T is not the square of any integer. This is one case. And if T is the square of some integer, say T is equal to S square, where S is an integer, then this set will consist of minus s and s. So that means if t is equal to s square for some s belonging to s. So this is the inverse image. Its description is slightly complicated, but it is what it is. So if t is equal to s square for some s belonging to s, keep in mind that now our s is the set of integers. So we are not just requiring t to be the square of some real number. No, it has to be the square of some integer, because t itself is an integer. So, and our domain S is the set of integers. So if this happens, then t has two square roots as usual, just like this one, but now they are minus s and s. So you can see why this function is not one-to-one and is neither one-to-one nor onto from here also. It is not onto because sometimes this inverse image is empty, and it is not one-to-one because sometimes this inverse image has two elements. And finally we come to part D. So in part D, our sets are the same, just like part C, but the formula for the function has changed. So for D, this function is one-to-one but not onto. Okay, let us first say why it's not onto. Sigma is not onto because there is no integer s such that 2s is equal to 3. All the images are even integers. So this odd integer 3 cannot be an image, and that you can see from here also. If you assume that such an s exists, then that s, if you solve this equation in the system of real numbers or rational numbers, you get s equal to 3 by 2, which is not an integer. So that's why sigma is not onto. However, sigma is one-to-one. Because for any two distinct elements s1 and s2 belonging to s, that means any two distinct integers, we have s1 sigma which is equal to 2s1 is not equal to 2s2 because s1 and s2 are not equal to s2 sigma. So distinct elements have distinct images, so that's why it is one-to-one. Okay, now what about the inverse image? For any t belonging to t, we have, since images consist of all even integers, so the inverse image of some element will be non-empty if that element is an even integer, otherwise it will be empty. we have, so here also we need to write a formula like this, so we need space. T sigma inverse is empty if T is odd, because T is coming from capital T, which is also the set of integers. So T will be either even or odd. If T is odd, then this is empty, just like here. For 3 sigma inverse is empty. There is no S for which 2S is equal to 3. But if T is even, then the inverse image consists of this single element T by 2 if T is even. Okay, so this completes the solution. Now we go to the second one. If S and T are two non-empty sets, prove that there is a one-to-one correspondence between S cross T and T cross S. One-to-one correspondence means a mapping that is both one-to-one and onto. So we have to show that such a mapping or a function exists between these two Cartesian products. Okay. Define f from S cross T to T cross S by this. This ordered pair is mapped onto the one which is obtained by interchanging the coordinates. So that means this is an ordered pair here. So S is coming from S and T is coming from T. So that means this will belong to T cross S. Also, for this given ordered pair, the image is unique. There is only one such image. So that means this function is well defined. Clearly, f is well defined. F is also one-to-one and onto, it can be easily seen, but since we are solving a problem, an exercise, we have to do it. For any A comma B belonging to T cross S, we have B comma A. If A comma B belongs to T cross S, that means A belongs to T and B belongs to S. So B comma A will belong to S cross T, such that B comma F A, B comma A F is equal to A comma B. So we have realized this element in the second set as the image of some element in the first set. Hence, F is onto. Next, for two elements S1, T1 and S2, T2 belonging to S cross T, assume that their images are equal. If we can prove that the elements are also equal, then that will prove that the mapping F is 1-to-1. So we are assuming that S1 T1 F is equal to S2 T2 F. Okay, so this is our assumption for proving one-to-oneness. This implies S1 T1 F means T1 S1 and S2 T2 F means T2 S2. Which in turn implies T1 is equal to T2 and S1 is equal to S2. This is just the condition for two ordered pairs to be equal. But then, by that same condition, S1, T1 will be equal to S2, T2. Hence, F is 1-to-1. Being both onto and 1-to-1, F is now a 1-to-1 correspondence. I am not writing that, okay. So if you want, you can add that one more sentence at the end of this solution. Hence, F is a 1-to-1 correspondence between S cross T and T cross S. Okay, now we come to the third one, which is also similar to this one. If S, T and U are non-empty sets, prove that there exists a one-to-one correspondence between, there are two parts. Part A says S cross T cross U and S cross T cross U, and part B says either set in part A and the set of all ordered triples s comma t comma u. Just like ordered pairs, we also have the concept of ordered triples, or in fact an ordered set of any finite number of elements, and sometimes also infinite number of elements, but let's just leave those things. We have an object like this, where S belongs to S, T belongs to T, and U belongs to U. This one I will not solve fully. I will just mention the functions and you prove that they are one-to-one correspondences, just like this. The proofs will be somewhat more lengthy than this one, but after all they are not very difficult or something that is very different from this one. They are quite similar. So the solution is this. Define or okay, there are two parts, no? So I have to mention A and B separately. Let me just do the first one, then you will understand how to do the second one. Define a function or a mapping from S cross T cross U into S cross T cross U by, be very careful in writing an arbitrary element here. This is actually a Cartesian product of two sets. One of them is S cross T and the other is U. So one of the sets is itself a Cartesian product of two more sets, S and T. So an arbitrary element here will look like this. After all, it's an ordered pair of two objects. The first object or the first coordinate is itself an ordered pair because it has to come from here, right? And the second one is an ordinary element in U. Now in this one, in the first one again, this S has to come from S and T has to come from T. So I will map this to, naturally you can almost guess what this other one will be. The image will be S comma T comma U. Now note that this is an ordered pair in this, so it's a legitimate element in this, and that's why, and since S belongs to S, so this is ultimately an element in this. Further, because for this element which I am mapping onto something, this is unique, you can clearly see why it is so. The mapping is well defined. We keep on writing clearly because it is clear here. Sometimes it will not be so clear. In those cases, we have to explicitly show that the mapping is well defined. Okay, excuse me. So clearly, F is well defined. For any element here, say I take it as A comma B comma C belonging to S cross T cross U, there exists. So now I am going to show that my function or mapping F is onto. So I proceed just like this one. Although I am going to wrap this up, but you have already seen what we have done here in the previous solution. So there exists. Note that now A belongs to S and B comma C belongs to T cross u. So B belongs to T and C belongs to U. That means this ordered pair of A comma B and C belongs to S cross T cross U, such that A, B, C, F is equal to A, B, C according to our function. Hence, F is onto. Okay. Next, the structure of the solution is, you can see it's just like the previous one. Next, we will take two elements in the first set, assume that their F images are equal and show that the elements themselves are equal. That will prove that F is 1 to 1. Next, let S1 comma T1 comma U1 comma S2 comma T2 comma U2 belong to S cross T cross U, such that their F images are equal. Okay, then so according to the definition of this function, we now have S1 comma T1 comma U1 is equal to S2 comma T2 comma U2. This implies, okay, so first we apply the definition of equality of these two ordered pairs. Note that this is not an ordered triple, it's an ordered pair because we have only one comma separating two objects. So that's why it is an ordered pair. So applying the definition of equality, we first get S1 equal to S2. First coordinates are equal and second coordinates are equal. From this, we get, we already have the first equation, so let us just again write it. Now additionally, from the equality of these two ordered pairs, we have T1 equal to T2 and U1 equal to U2. Thus, since these two are from the first two equations, we can now write S1 comma T1 is equal to S2 comma T2 and U1 equal to U2. And then again from these two equations, so finally we can write this. Is equal to S2 comma T2 comma U2. So the assumption that the images of these two elements are equal led us to conclude that the elements themselves are equal. So that's why F is 1 to 1. and hence f is a one-to-one correspondence. Now next in part B we have to prove that there is a one-to-one correspondence between this one and the set of triples that has been mentioned here, and also between this one and this set of triples. Okay, it's enough to show that because of the first part, it's enough to show that there is only there is a one-to-one correspondence between this one and this one, because then automatically using that and this we can create a one-to-one correspondence between this and this. So here I will not fully do it, I will just mention the mapping, define. Oh, but before that I need a notation for the, see, this is the one thing I don't like about Herstein. He does not define enough notations. Writing becomes very cumbersome because of this.